So for our first one here, 5 times the fourth root of x minus 7 equals 18. Where do we start? We add 7. Very good. So the 7's gone. So we're left here with 5 times the fourth root of x. Now I really don't need the multiplication symbol there, but I put it there just so that it's very clear that that is not 5 to the fourth power, that the 4 is the index of the root. 18 plus 7, of course, is 25. Then what? 5 by the 5. Very good. We divide out that 5. We now have the fourth root of x. What's 25 divided by 5? 5. Okay, Jordan, what's next? What's left? How do we get rid of the fourth root? Fourth power. Good job, Ian. So the fourth power of a fourth root, remember, cancel out. Fourth root and fourth power cancel out because they are inverses, just like adding and subtracting the same number would be. 5 to the fourth power is 625. So that is 625. Over here, what do we do first? Subtract the 11. So x to the fifth over 4 equals 8. And then x to the fifth divided by 4, what do we have to get rid of next? The 4. It's dividing, so we get rid of it by multiplying it. So we're left with x to the fifth there. 8 to the fourth is 32. And then what's the inverse of fifth power? The fifth root. So the fifth root and the fifth power cancel out. We're left with x. Fifth root of 32 is 2. I purposely did an odd root there. That way we didn't have to worry about that possibility of a positive and a negative. An odd root, remember, is always just a single real answer. If this were a college algebra class, by the way, we'd go through the fact that a fifth root always has 5 answers. But we're not going to get into that. 4 of those 5 answers are imaginary numbers, complex numbers. Okay, then. Anybody have any questions off the homework and stuff for the powers and roots, the exponentials? What do you have? So page 465, number 20. So we've got 10 to the power of negative 0.5. Well, I'm going to rewrite this as 10 to the power of a negative 1/2. There are 3 things going on here. Remember, and we didn't necessarily put all these together yesterday. The first thing that's going on is that negative power. Remember, we talked yesterday about 10 to the negative third is the reciprocal of 10 to the third. So that's what this is. 10 to the power of negative 1/2 is the reciprocal of 10 to the power of 1/2. Oops, no negative, just 1/2. Now, the power then, the top number, the numerator is a power. Well, what's 10 to the power of 1? Just 10. The denominator is the index of a root. So what that is saying is the square root of 10. So it's 1 over the square root of 10. 1 divided by the square root of 10, which gives us 0.3162. You could have done that, and it should give you the same thing. You just punch her in. Any others? 30. 30. Number 30. Ooh, that's a good one. These guys have been with me long enough to know that's never a good thing. Right? Negative 27 over 8, the power of negative 1/3. Now, here's what I'm going to do first. I'm going to do the negative, because the negative means reciprocal. So I'm going to take the reciprocal of this. So that's going to be 8 over negative 27 to the power of 1/3. Now, the power of 1/3 means third root of 8 over negative 27. Third root, then, of course, can be split. Third root of 8 over the third root of negative 27. Third root of 8 is 2, and negative 20, third root of negative 27, negative 3. So the answer is a negative 2/3. Any others? None of them like number 40 with the flux density or anything like that? Okay, well, today we are going to look at a different type of inverses, a new set of operations. Our new set of operations is going to look like this. Instead of x to the power of 2, we're going to have 2 to the power of x. Now, this was called an exponent. This is called, very closely related, exponential. And there is a difference. Now, the inverse of our exponent was a root. X squared, the opposite was the square root. For our exponential, the opposite is going to be a log, base 2, or base whatever our base is. So over the next several days, we're going to be talking about exponentials, a number to the power of x. So our variable is going to be in the power part of the exponent now instead of the base. And then we'll look at logs as the inverse of those. So let's take a look at y equals b to the power of x. That is our basic form of an exponential equation. This form is very, very important in electronics, very important in a lot of scientific fields, in fact. Let's do a little bit of graphing work with this thing. So somebody pick a number between 2 and 5. I heard 3. So we're going to use 3 for b. So y equals 3 to the power of x. And we're going to take a look at a graph here. So we're going to come up with values for x. Let's start out with like negative 3, maybe negative 1, 0, 1, and 3. Just taking some values spread across the graph. We may take more later if we need to. So if x is negative 3, that means y equals 3 to the power of negative 3. What is 3 to the power of negative 3? Yeah, 1/27 or 0.0333. Look familiar? That's not correct though, is it? No, 37. If x is negative 1, y is 3 to the power of negative 1, which of course is 0.33333333. If x is 0, y is 3 to the power of 0, which is 1. If x is 1, y is 3 to the power of 1, which is 3. If x is 3, y is 3 to the power of 3, which is 27. So on our graph, at -3, we're almost nothing. We're down just bigger than 0. At -1, we're at 1/3. At 0, we're at 1. At 1, we go all the way up to 3. At 3, we go all the way up to 27, which is off the top of our graph. If x were 2, what would 3 be? 9. 3 squared would be 9. So we get this curve here. That is called the exponential curve. A couple of very important things about this curve. One is you'll notice no matter how small x gets, x can be -100. This is never going to get below 0. Y will never be negative here. So this has what we call an asymptote. You don't need to necessarily know that word. All that means is the graph is never going to cross that line. It's never going to go below x or y equals 0 in this case. So the smaller x gets closer and closer and closer to 0, but it'll never quite get there. But on the other side here, you can see it gets large rather quickly after it gets into the positive numbers. And that is the property of an exponential. So that was y equals 3 to the power of x. What if I have y equals 0.5 to the power of x? Let's just pick some numbers. If x is -3, y is 0.5 to the power of -3, which is going to be 8. Very good. If x is -1, y is 0.5 to the power of -1, which is 2. How about if x is 0? Yeah, anything to the power of 0 is 1. If x is a positive 1, 0.5 to the power of 1 is 0.5 or 1/2. How about if x is positive 3, 0.5 to the power of 3 is 0.125. Now we see here that our graph goes very differently here. At -3, we're at +8. -1, we're at +2. 0, of course, is still 1. At 1, we're at 0.5, and at 3, we're at 1/8. It looks to be a very similar curve, but what's the difference here? Yeah, it starts high and goes low. As we get into the negative numbers, it goes high. As we get into the positive numbers, the larger the positive number gets, the closer and closer we get to 0. This type of a curve up here, where the curve gets large really quick as the numbers get larger, and it goes to 0 as the numbers get further negative, is called exponential growth. That's how interest builds in an account. Anything that has a constant percentage increase will look like that. This here, where it gets smaller, and then as the numbers get larger, it gets closer and closer to 0, is called exponential decay. This one is actually quite important to you guys because this is how the charge on a capacitor decays. The more charge is on there, the faster it discharges. But as the charge decreases, it discharges slower and slower and slower until it hits nothing. If you look at these equations, though, both of them were of the form y equals b to the power of x. So what made one of them do growth and one of them do decay. Y equals 3 to the x was growth. Y equals 0.5 to the x was decay. Oops. What's the only difference between the two of them? This one's a whole number, this one's a decimal. In fact, the main difference is this one here, that value for b is greater than 1. And this one, that value for b is less than 1. That's very important. So what are some applications of this stuff? Well, let's look at decay first of all. In fact, to look at decay, I want to look at some similarities with what we've learned with our powers earlier, or exponents earlier. So what I basically just did, y equals 0.5 to the power of x, is this, y equals 1/2 to the power of x. How would that be different from y equals 2 to the power of negative x? Would it be different? What does that negative power mean? Remember, a negative power means reciprocal. What's the reciprocal of 2? 1/2. So if we don't want to write a fraction, 1/2, we can use that negative power. So we talked up here, we mentioned that if b is bigger than 1, it's growth. If b is less than 1, it's decay. That only applies as long as the power is x. It's a positive x, not negative. If we have a negative power on the x, it reverses that because it turns everything into a reciprocal. So if I have y equals 0.3 to the power of negative x, is that going to be growth or decay? Careful. This is less than 1, so it looks like it should be decay, but the power is negative, so it's going to be reciprocal. So that is actually growth. If we have y equals 5 to the power of negative x, growth or decay? Yeah, the 5 is bigger than 1, but it's a negative power, so it's really a 1/5. So that is decay. Y equals 0.2 to the power of x, growth or decay? That is decay. It's less than 1, and it is a positive x, so it is decay. Basically, why this is decay is because that 5, because it's a negative, is behaving as a 1/5. Here, that 0.3, because that's a negative, is behaving like 1/3 or a 3 1/3, or 1/0.3 or 3 1/3. So in these two cases here, this is actually a value of b that's bigger than 1, even though it looks like it's 0.3 because that negative power, it really is 3 1/3. And this is a value of b that's smaller than 1, even though it's 5, because of the negative power, the reciprocal makes it a 1/5. So you have to be careful that your power of x is positive before you make that determination. So then, back to exponential decay. Exponential decay occurs a lot on, like I said, in your inductive circuits and your capacitive circuits. And we'll actually look at ways of doing exponential decay coming up. But we're going to look at something a little bit simpler than those for right now, and that is half-life. Half-life is for mostly for radioactive materials, but there are other materials that actually will decay at a very given rate. If you have accounts that are losing value at a certain percentage for a period of time, things like that will also experience a half-life. But let's say we're looking at radioactive material. Radioactive material, the half-life is literally the length of time it takes for that material to get to, for half of it to decay and disappear. So if you had 800 grams of material to start out with, the half-life is the time it would take for it to deteriorate to 400 grams. So let's say this material has a half-life of 48 days. The formula then for the amount of material there would be y equals 1/2. I should be careful. That a with the little zero there is the starting amount. Sometimes you put y with a little zero there. We're just going to say a times 1/2 to our power of time, but it's going to be t over 48 because the 1/2 only occurs every 48 days. So we're going to divide that by 48. And of course, t here must be in days because our half-life is in days. So we're starting with 800 grams of material. How much would be there after 10 days? So in our formula, we're going to put in here y equals 800 for 800 grams times 1/2 to the power of t over 48. What goes in for t? 10. So I got to get my t out of there and put in 10. So to enter this in the calculator, we got to be careful. 800 times, oops, get out of there. 800 times, we're going to put 1/2 in parentheses to the power of 10 divided by 4. Many of your calculators, you'd have to put parentheses around this power. So to the power of, you'd have to put parentheses 10 divided by 48. I get 692.43. That is in grams, the same unit as the 800. An alternative way of expressing this formula. We talked about up above that positive or negative power on our variable. I could put this as y equals that initial amount. Instead of times 1/2 to the power of t over our half-life, it would be times 2 to the power of negative t divided by our half-life. Let's take a look at that. So we do the same thing, 800 grams times 2 to the power of, and we're going to go negative 10 divided by 48. And we see it gives us that same answer, 692. So those formulas are equivalent, and either form can be used. So for a material, well, let's try that again. Material with half-life of 72 hours. How much would remain after 24 hours if the original amount is 2,500 grams. Tell me what to do to set this up. $2,500 times 1/2. (24/72). There you go. So 2,500 times 1/2 in parentheses to the power of, oops, 24/72 in my power. 1984.25 grams. Here's one to try in your notes. Starting with 1,400 grams of material with half-life of 9 days. How much is left after 27 days? I'll give you a second to figure that out. What's that? Perfect. I'll let everybody else give it a shot, see if they can get it. Yeah. Good enough. What is our formula? Jordan? Y equals, what do we start out with? The initial amount in this problem would be 1,400. Very good. Times 1/2 to the power of, this is the time over the half-life. So what's our time here? 27/9. Very good. So 1,400 times, I'll put the 1/2 in parentheses, the power of 27 divided by 9. It is, Ian is absolutely correct. It is 175. Now we could have also, by the way, just like we could have up there, if we didn't want to have to put that 1/2 in our calculator, we could have done 1,400 times 2 to the power of -27/9. Give us the same thing. So it gives 175. Let's take a look at this and reason through it. What does the half-life stand for again? The time it takes for the material to decay to half of what it was, right? So we started out with 1,400 grams. How long is the half-life here? 9 days. At 9 days, how much should be left? What's half of 1,400? 700. After another 9 days, so that's a total of 18 days, what should be left? Half the 700 is 350. After another, 9 days, which is our total of 27 days, what should be left? Yeah, half of 350 is 175 grams. Does that make sense? Let's look at another problem here. You have 240 grams of material with half-life of 12 minutes. How much is left after 30 minutes? Now, before we answer this one, let's reason this out a little bit. We've got our 240 grams, right? Our half-life is 12 minutes. So after 12 minutes, how much should we have left? 120. After another 12 minutes, or a total of 24 minutes, how much should we have left? 60. After another 12 minutes, or a total of 36 minutes, how much should we have left? Half of 60 makes 30. Well, we're looking at 30 minutes here. That's between 24 and 36. So that's telling us our answer better be between 60 grams and 30 grams. So let's put this in our formula and try. Y equals, now I'm going to start the formula. You guys are going to have to finish it. 240 times 2 to the power of what? Negative 30 over 12. Very good. Why do we have to use the negative 30? Because I used the 2 instead of the 1/2. So 240 times 2 to the power of negative 30 divided by 12. 42.43. And we see that is between the 60 and the 30. So that is, we know that we're in probably in the right area there, right ballpark at least. Any questions there? Okay, well then let's take a look at growth. Growth typically takes the form of like an interest or something like that. Let's say that Social Security has a 3% annual cost of living increase. So what that means is if you have your Social Security at the start of the year, you get your increase. That's going to give you the amount you're going to get at the end, starting at the end of the year. So if you take that starting value as 100%, our increase is 3%. What's your ending value going to be for that year? 103%. Now we're going to use the rate method of percent. 103 as a rate is 1.03, is equivalent to 103%. So we're going to take an initial amount. Let's say that we start with, right now, you are receiving $1,700 a month. And let's say you just received your increase. So how much will that be in 4 years? So after 4 more increases. Well, this amount, excuse me, Y is going to equal to that initial amount, in this case the 1,700, times 1.03 to the power of 4. giving us $1913.36. So $1,913.36. Now, the key to adapting this to more general problems is this piece right here. That is your growth factor. And more specifically, it's your growth factor per period. I specifically chose this example of Social Security because they only give you that increase once a year. But what if it's given at different periods of time, like compound interest? Let's say you invest $5,000 at 8% compounded quarterly for 5 years. The formula that governs this, y is equal to that initial amount times that factor, that compound interest factor, that rate per period, to the power of the number of periods. And the reason I wrote them out in words for right now is there are going to be some considerations here. That initial amount is always the same. That factor is 100% plus an increase per period. But 8% is not going to be your increase per period. That's the annual rate. It's compounded quarterly. So what we would do is we would divide that by the number of periods in a year. So it's R over K, where K is the number of periods in a year. If it's quarterly, K would be what? 4, right? 4 quarters in a year. To the power of the number of periods. Well, the number of periods is not just the number of years. There's 4 periods in every year, so it's going to be K times T. So for this problem, it's our $5,000 initially times 1 plus 8% has to be written as a rate, 0.08, divided by 4 to the power of 4 times 5. Giving us 74, 29, 74. So at the end of 5 years, that would be $7,429.74. That's 4 times 5. Yep. That's K times T. K is 4 times a year because it's compounded quarterly, and T is 5 years. Now, we got just a little bit of time left, but I want to introduce you to a magic number. E. Remember last semester we had that natural constant pi? Pi was the 3.14159 blah, 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 right? That was the ratio between the circumference of a circle and the diameter of a circle. E, I got a little squeaky there, is called the natural constant. It actually comes from a complex series that I don't want to get into right now. But, well, why not? It's actually the series of 1 plus 1 over n to the power of n as n goes to infinity. We haven't studied limits in here, so that probably isn't a huge meaning to you. But it's a natural constant. And for some reason, there are all sorts of things in nature that follow that constant for their growth and for decay. The number E, by the way, can be found on your calculator. Many of you have an ln key on your calculator. Right above it, you have an EX key. It's a second function. So if you hit second, and then the ln key or the EX key, Usually it gives you e to the power. You have to put power of 1 in there. It equals, and it gives you that 2.718281828. That is the natural constant, e. That's the value of e by itself. Well, we almost always use e in some sort of exponential or logarithmic equation. So e governs the decay of voltage in a capacitive circuit. So the voltage in a capacitive circuit is equal to the initial voltage times e to the power of negative t divided by RC, where R is the resistance and C is the capacitance. Now I'm actually going to try to be technically correct here. So this is a circuit that we have. Let's say we're going to start out with 120 volt source. We have a resistance here of 2.5 kilo ohms. Capacitance here of 1.5 millihenries. Henries isn't right for capacitance, it's farads. Henries is for an inductor. So anyway, let's say find the voltage. What we've done is we've totally charged this circuit. And now we're going to take out the voltage source and we're going to close it. We're going to let that capacitor discharge. Well, the maximum voltage on that capacitor is equal to our voltage source. It's charged up to 120 volts. So I want to find the voltage after, let's go 0.2 seconds of discharging. So our initial voltage was the full 120 volts times e to the power of negative 0.2 divided by 2,500 ohms, 2.5 kilo ohms, times 0.001 farads. So I have 120 times, I have to do that second ln or second e to the power of, and then there I'm going to do in parentheses. Now, in many of your calculators, you're going to need two sets of parentheses in this exponent, this power. Negative 0.2 divided by, then you need another open parentheses, 2,500 times 0.0015. Then you have to close your parentheses twice within your exponent. That gives you 113.77. So after 0.2 of a second, that capacitor is now discharged down to 113.77 volts. We will talk about these more tomorrow. For right now, they are on page 469 of your packet. 1 through 25, the odds. Any questions? This is the fun stuff.